Hello, this is Siddhartha-Jana, a member of the Energy Efficient HPC Working Group. And the intention of this recording is to update the HPC community about some of the latest findings from a year-long survey. This survey started in mid-2016, ran all the way through 2017, and really the focus of this survey was to try to understand what are some of the active investments in the field of energy and power-aware management. And this survey was targeting HPC sites across the globe. So the goal was to try to understand how much are they actually investing in this field, and especially in the field of adding this power and energy awareness within job schedulers and resource managers. So by job schedulers, what I'm referring to are system-wide software agents that run either in a centralized or a distributed manner, and that are responsible for controlling and monitoring the job behavior, its execution, and then even reporting back to the users if there are any errors. Now, when you're trying to introduce this concept of energy and power awareness within such software agents, there is a need to try to understand how much of it is feasible, because HPC sites usually have machines that usually are built by more than one vendors. There really needs to be a clear understanding of what becomes the responsibility of the vendors in the hardware stack, and what kind of responsibilities need to be added into the software stack in order to maintain energy efficiency. Now, a quick background of the team that conducted this survey. So this is a sub-team. The Energy and Power Aware JSRM team is a sub-team under the Energy Efficient HPC Working Group, which comprises of HPC center and facility representatives, representatives of academia and research institutes, and also vendors. And really the goal of this team, this overall working group, is to try to assess the environment, computational, and usage drivers that actually motivate power management efforts within the group. Linked to the results of the survey and the white paper, a poster, are all in the description below. But for the purpose of this talk, let me quickly summarize the key takeaways from the white paper. That is what I intend to do, along with an interest in soliciting feedback from the community for next steps and future roadmaps, right? So now, if you have to try to drive energy and power awareness from the job schedulers, you need to try to ask the question that why should you even look at the software in the first place, right? So if you look at the top 500 first ranking systems across over a decade, what you would notice is that if you have to try to reach the exascale mark, if going by the current technology trends, having meeting the 20 to 25 megawatt power limit is really a big challenge at this point. So really, you will need up to an order of magnitude improvement within a period of, say, 5-6 years to be able to actually hope to achieve exascale within a power budget. So instead of just relying on the hardware stack, now the need arises to try to actually introduce some kind of intelligence within the software stack as well. So before I dive into the actual details of the survey, a quick point that needs to be noted, which is that the scope of this survey was not to focus on the entire HPC facility plant that actually houses an HPC system. So when you try to look at power management issues, there are issues concerning the HPC system itself, and there are equally daunting challenges when it comes to handling the secondary infrastructure that supports those systems. Things like cooling and other HPC resources and facility management. All of those secondary factors were not part of this survey. So this survey just focused on the actual HPC machine and some of the challenges and some of the characteristics that come with that, with just looking at this machine. And that's the scope of the survey, and that was what the scope of this talk will be. So as mentioned previously, a number of different global sites were surveyed, Many of the HPC centers, they came forward and actively participated, and we were thankful of that. Only then could the survey be treated as success. So if you note on the left, I have listed many different sites that participated. Countries included France, Italy, Japan, Saudi Arabia, United Kingdom, and the United States. And really the criteria for including these sites in the survey was as follows. So each of the sites needed to actively pursue a job scheduling and resource management solution that had some tendency of doing energy and power aware management. There was also a need for the site to actually target an HPC system, a large-scale HPC system, and then the ultimate goal that each of these sites had to have was the interest in actually investing in technology development and seeing that these solutions actually enter the production and computing environment and not just be a research-only project. Now, the survey, of course, comprised of multiple questions, but for the purpose of this talk, I will touch these following points. The first point that was really very crucial for this survey was to try to understand what was the actual motivation for these sites when they invested in these solutions. Another challenge was, and another question was really trying to understand what is the actual design and implementation techniques adopted by the sites. The results and the challenges, some of the lessons that they learned is also something that was brought out from the survey. And then also the next steps that the site intends to take once that they have started putting money into these efforts. All the details, of course, can be found in this white paper. Again, results and details in the description and also in this link on this slide. So let us start with the summary of the survey, right? So first point, as I mentioned, was trying to understand the motivation behind actually investing money into these energy power aware solutions. So we realized that the motivation really is drastically different from one site to another. Some of the sites reported that the reason they are investing money in this is because there were actual power constraints that came due to external factors like natural disasters, tsunamis, earthquakes. These were a genuine concern, and this led to government mandating specific limits. There were, of course, limits of operation costs, and then due to the shortage of electricity, the sites felt the need to invest in this direction. There were also power limits for some sites which were imposed due to internal infrastructure limitations. Just the design of the facility plan was such that they had this hard limit, and they have an active need to ensure that their system runs under a budget. Some of the sites who did not necessarily have a government mandated limit still wanted to stay ahead of the game because they anticipate that going ahead, because there will be a shortage of power, there needs to be some kind of investment done in trying to ensure that any kind of solution that is implemented on the system, that solution should lead to predictable, stable, and reliable results. And without that, doing dynamic power management is a big concern. And that is why some of the sites wanted to invest research efforts in this direction. Another challenge, of course, is the prioritization of high compute power. So many of the sites felt it necessary to try to limit additional secondary costs on power, and hopefully these power savings or this money savings that they achieve, they wanted to drive these savings into buying additional computational units. So the goal was really to try to improve your system computational throughput by limiting additional secondary infrastructure costs. Another major motivation was to try to understand the behavior of users when they try to run these large-scale applications, right? So one of the concerns that we have in the software stack is that if you have to try to write an energy efficient application, one of the questions out there is that how much can users be able to actually gauge their application behavior, and how well are they able to predict how much energy is being consumed. the way things are right now, the general consensus is that the users should not be really expected to participate that much when it comes to trying to design their applications. At the end of the day, they are scientists who need to do their science, and therefore there is a need for the sites to try to understand what kind of user applications are out there and what kind of typical behavior those applications have, so that they can tune their sites, their systems at their sites to the power requirements of the applications. Another noble motivation really is the need to be ecologically responsible, right? So being the desire to be green, reducing your carbon footprint when you're doing science is an active concern. And that was the motivation for some of the sites. Now, before I dive into the actual implementation and nitty-gritty details, let me give a quick overview of the type of system that we have in mind when we are trying to look at such solutions, right? So what is depicted on the slide here is a traditional HPC system where if you have to try to look at doing system-wide energy and power management, you have to try to look at what are the existing software agents out there already running in these current machines. Such software agents that can actually monitor more than one computational node, right? So site-wide, system-wide software agents that can monitor and control and keep track of resources is a good target where you can introduce such power and energy awareness. 3 different software agents stand out. You have the traditional job scheduler and resource management that is responsible for monitoring compute nodes and memory usage. But then you have some secondary system-wide agents as well, like say the IO servers, right, which are responsible for large-scale incoming input-output read and write requests, and all of these requests need to go to secondary storage servers. And there is this IO server that caters to all of these resource system-wide requests, IO requests. Another software agent that usually is not highlighted is the Fabric Manager. Now, Fabric Manager, as we may be aware, runs on a separate node, separate machine that keeps track of the health status of all your network resources. So your network cards, your switches, your routers onto the system, how active they are, whether some of them have entered into idle states, have some of them shut down completely. These all are monitored by the Fabric Manager. All the sites we interviewed, all of them are directing their power and energy management efforts to just the traditional job schedulers and the resource management. Each of their solutions usually involve, these very generic steps, which includes monitoring the different compute and memory resources, either through some sensors or some kind of regression models, and then also having some kind of mechanism of controlling the power on the actual hardware platform. These mechanisms can, of course, be triggered through hardware or software. They can be manually triggered by system administrators or end users, or it could be software, right, that's running within the job scheduler that could trigger these power management mechanisms. And then really the goal is to try to understand what is the actual implementation that the different sites are looking at. And a quick note before diving into the implementation, all the sites that we interviewed use some kind of sensors, actual physical hardware probes, or some kind of hardware platform generated interfaces, which were either in-band or out-of-band monitoring solutions, and that dealt with direct real-time measurements, right? In addition, some of the sites, in addition to just looking at power and energy, some of the sites also monitor thermal-based metrics like temperature, and then couple them with prediction models in order to get more accurate and fine-tuned information of power and energy values. Now, this slide attempts to summarize all the different approaches. it must be noted that each of these approaches are not mutually exclusive when it comes to their adaptation. So many of the sites reported using more than one or a combination of these approaches within their sites. So the first approach here, which was an interesting approach where the sites dynamically terminated jobs whenever they realized that their total system power consumption increased a certain fixed power limit, right? So this was a brute force approach that is currently being used for some sites. And really the main question there is, how do you even select what job to dynamically shut down? And in order to do that, a lot of different parameters like the job size, the job length, or the even priority of the users who are actually launching their applications. What is their user ID? All of these are also taken into account when you're trying to make decisions and selecting candidate jobs for termination. The challenge, of course, is to try to choose the right metric when you're selecting this job, right? There is no easy way of choosing which job should be shut down completely. And another challenge, of course, is that if you're dynamically shutting down jobs midway through their execution, all the energy and power that was consumed and that was invested in executing that application, all of them goes to waste, right? And you get zero science out of this approach if you shut down an application. Another approach is the automated reduction of node availability, where the idea there is if you have to try to reduce the power consumed by your total system, and if you see that your system is going beyond the threshold limit, what you do is you reduce the total number of compute resources in your system. So the idea is you completely shut down certain nodes and you remove them such that the users are not able to launch their applications on those nodes. Now, when you do that, what happens is you end up reducing the theoretical peak power that your system can consume, and that automatically reduces your dynamic power consumption of the entire system, right? The challenge, however, is that if you start removing compute nodes from your system, not physically remove them, but making them invisible to the users and making them unavailable for use, your total system availability drops down, right? And then already shut down nodes take time to boot up, and that is again a big concern. And you have to explain to the users why is it that their jobs are waiting in a job queue for a very long time. That becomes a concern. Another approach, unlike the first two approaches where the goal was really to either terminate jobs or to shut down nodes, the other approaches heavily rely on trying to leverage existing power management control knobs that are exposed by your hardware platform, right? So one approach is the use of power capping mechanisms. Now, power capping is really just a generic term which is used for trying to limit the power consumed by your hardware by specifically talking to the hardware and telling the hardware what power budget it needs to meet. And you do that typically by writing into specific registers, like model-specific registers. And of course, these solutions are heavily vendor dependent, right? Each vendor might have different interfaces or different set of registers that you can read or write into in order to force the hardware component to limit its power consumption. What this usually means under the hood is once you ask for a certain power budget, your hardware tries to do a number of things, which could include things like adjusting its voltage consumption or its voltage level, just to make sure that the power cap is met. Of course, this is not a guarantee. No hardware vendor actually guarantees that whatever you ask for is always what you will get. But the hardware needs to be intelligent enough to try to understand what the application actually needs versus what the user is actually asking for in terms of power. And then the hardware usually makes up its mind of how much power to actually, consume while it's operating. Now, different solutions were reported. Intel processors, for example, is a good example. Intel processors provide the RAPL interface, which stands for RAPL, running average power limiting, which is a mechanism that you can use to write into specific registers to limit its power consumption. There are other software tools and interfaces and frameworks available out there that you can use to leverage such hardware capabilities. Slurm's HDPM, Software Dynamic Power Management, and Cray's CapMC tools were two of the tools that were reported by these sites that were actually using these power capping mechanisms for Intel and non-Intel machines. One of the challenges reported with doing an out-of-band power management, right, is that while on one hand, because you're doing a system-wide power management approach and you're trying to pass commands of power control remotely, you are able to get a system-wide view, and therefore your job queue wait time was observed to drastically improve. In other words, get reduced. The downside, of course, was that there was heavy performance variability that was reported by using these out-of-band solutions. The sites reported that using in-band solutions where you're statically capping power, like Intel RAPL, directly if you're running your software control agent on your compute node, and if you're limiting power there, better performance variability dropped significantly. Your results were more reliable. The downside, of course, is that doing a per node power capping is not really going to give you, is not going to be helpful when you're trying to save. It will contribute to saving power consumed by the entire system, but you will not have a system-wide view when you're trying to do just a per node power capping. So there still exists this need within the community to come up with this centralized system-wide agent, that is capable of doing power capping in a more reliable, reproducible manner, but at the same time ensuring that the entire system status is taken into account when such decisions are made. The next approach number 4 was that was reported by the sites was the use of P states, C states, and S states. Now these states are usually operating states of different hardware components, which are exposed again by different hardware vendors, and they are implementation specific. P states relate to power performance states of processors, for example, where each of these states actually correspond to different operating frequencies of your CPU, and different operating frequencies in turn map to different voltage levels. So if you know that your application is not really does not really need to run at the fastest speed possible, what you can do is ask your hardware platform to run at a slower frequency, thereby leading to more energy savings. Now, in addition to that, there are two other states, C states and S states, which relate not necessarily to processor activity, but are make more sense when you're talking about hardware components that are not doing any activity, right? So when your hardware component is not running any application, you could essentially put them to lower power states, and those are what C states and S states correspond to. Now, the challenge reported with using P states as a mechanism for saving energy and power is that there are concerns among users and system administrators that trying to limit your CPU frequency in an incorrect manner would lead to impact in performance, right? So performance degradation is expected if you are incorrectly setting your CPUs to the wrong frequency values. So really, again, a need arises within the community to come up with some kind of software framework that actually tries to take intelligent decisions of changing P states without impacting application performance. Another concern is that when you're actually putting things to lower frequency, there needs to be some kind of standardized user interfaces Different hardware platforms have different interfaces, and if your user or your job scheduler needs to set those P states, there needs to be a standard interface because there are different vendors in the software field and different vendors in the hardware field, and they need some common API to communicate with each other. C states and S states, because they relate to compute nodes that are idle anyway and not doing any application execution. So using them gives a big power savings, right? Because you're not affecting any performance because there is no activity that's going on. So it was reported by the users that using C states and S states definitely is a good solution, and they have achieved strong power savings with that approach. Slurm, IBM Load Levelers, Platform LSF were two of the tools or software frameworks that were reported as being used for this approach. In addition to these top 4 approaches, there is also the method of predicting how much power you're going to consume and then use that while you're trying to make decisions about allocating job resources. So static prediction models and the design of these are actively being looked into within the research departments of many of the sites that we surveyed. The goal is to do system-wide control and to implement this prediction model within the job schedulers and to use history of past application runs to try to learn from past behavior how much power was being consumed, what was the ideal P state at which the application ran while during its execution. IBM Load Leveler was one such software framework that was reported by the sites that was actively being used. The challenge, of course, with this approach, firstly, is that you have some kind of machine learning technique or some kind of prediction model that requires you to have training data, which means you have to run your applications multiple times under different system configuration, and you need to maintain that history and database. And also, if you have to come up with a prediction model, you need to choose the correct set of input parameters that will drive this model, right? All of these are challenges. So if you have a new application that comes out of the blue, the usability of this prediction model becomes questionable. One last approach that was reported by some of the sites was the approach of actually tagging applications with some specific tag value, right? So really by tag value, all this quote unquote tag corresponds to is some kind of identifier for an application, such that when this application is assigned this tag value, your job scheduler or your system-wide resource manager can associate the application's behavior with that tag value. So each tag value could essentially correspond to some ideal P state, an ideal frequency, or ideal power cap. And then once it sees that tag value associated with an application, the job scheduler could set the system configuration according to those parameters and the tag value. And then, your application can run in that environment. Now, the concern, of course, is that when you're trying to map tag values to applications, the way you do this is questionable, because now you're actually relying on the users to know their application, and the expectation is that users know their applications best, and how much power they consume is something that the users also know. So they should be the right person to try to tag their application. Now, this is the thought process with this approach, which might not necessarily lead to good results, because the concern really is that how much can your end users actually know about power and energy usage when it comes to applications. And also there is this need for maintaining this historical record where each tag value needs to correspond to different system configuration parameters, and then your application needs to be mapped to those tag values. So after these approaches, really there seems to be this really active drive among all these participating sites to explore further, invest more in their research, and also actually invest more in technology deployments using some of the approaches discussed above, or a combination of approaches discussed above. The goal is to use the lessons learned and the results obtained in actual procurement documents in the future. There's a strong interest to continue development and deployment. The long-term goal for many of these sites include things like improving their power estimator. So some of the sites reported as coming up with some kind of prediction model to estimate how much power their application is going to need. And that is an active area of research where you look at your application and try to estimate its power. Another long-term goal for some of the sites is to try, when they're using these power capping mechanisms, where you're telling the hardware what power cap you should run at. Such power capping mechanisms, currently they are looking into only system level granularity, but the goal long term is to try to also incorporate multiple other machines that are hosted in the same site when they are trying to do power capping, because at the end of the day, your power budget is for the entire facility, right? And not necessarily just for one system. Other long-term goals include incorporating secondary infrastructure costs when you're trying to do power management. So it's not just your computational resources or your HPC system that consumes power, but then your additional facility infrastructure like your cooling tower, and then your PDUs and your secondary power supply units. All of these also consume a lot of power. And if you have to do facility-wide power management, these additional secondary infrastructure costs also need to be taken into account. So this was a pretty successful survey. We had a white paper that was published during the Supercomputing conference in Denver. Again, links are in the description. We had a birds of a feather session. There was a poster session. There was also active discussions during the energy efficiency HPC working group workshop, and also at the exhibition booth in the exhibit floor. Going ahead, really, there are many questions for the sites, for the vendors, and for the communities out there. And a note to the viewer of this video, if you fall in any of these categories, we would really appreciate your input. So please get in touch with us, details in the description. So for the sites, a number of questions arise, like if you have to try to implement power-aware and energy management solutions, at what level of granularity would you like your users to go to when you're doing power management? Or would you like your software stack to go to? Would you like to limit your power consumed to just at the job level? Or would you rather limit power at the node and socket level? Will you let your operating system expose interfaces so that users can specifically talk to your hardware and limit and tune some of those power performance knobs? These are questions that HPC site administrators need to answer, and system administrators need to do. Other questions include, if you have to, what kind of results would you, or what kind of opportunity analysis data would you like to see when you're trying to make these decisions, right? Of what granularity should your power management be? That is a question out there. For vendors of schedulers, really the question is, have you thought about designing good interfaces, standardizing those interfaces when it comes to limiting power, or asking your system administrator or your user to set a power budget? Have you thought of good interfaces? There are also concerns about topology-aware placement, because job schedulers and resource managers are responsible for placing jobs and allocating nodes to those jobs. Topology awareness becomes a concern when it comes to power savings, because better placement leads to better performance, leads to reduction in time spent doing data movement, and all of that ultimately lead to power savings. For operating system vendors, There needs to be kernel modules that let you control the power and energy knobs on the hardware platform. So currently users need to either run as root, or they need to install some other third-party open source or closed source kernel modules that let you actually interface with these control knobs. But really, if your operating system and power management, if your operating system needs to become more power aware, you need to drive these kernel modules within your actual software source code. So that's one concern. System component vendors, hardware vendors, CPU chip manufacturers. Well, you all need to improve the interfaces for setting and reading power and energy control knobs and MSRs. This is a well-established concept. This is nothing new. It's just that, and all the vendors are working tirelessly, I'm sure, towards this direction. But more of this needs to happen. Better documentation needs to come out. For the community, really, we need to come close together. Academia, government, national labs, we all need to come together to try to standardize some of these interfaces, because if future HPC systems are going to be built with different components that are made by different vendors and different software components that are also supplied by different vendors, in that case, if you need to do the system-wide power management, there needs to be this fluid API or this good standardized interface so that one vendor's solution can talk to another vendor's component. There is also a need for additional surveys. Please, again, dear listener, if you have additional feedback or comments, or if you would like to see more surveys done, if you would like to determine what the next steps after these surveys are, please get back to us and we can collaborate. Closing thoughts, do get in touch with us. Details in the description below. Again, I'm Siddhartha.Jana. Here's my email address. The Energy Efficient HPC Working Group co-chair is Natalie Bates, and please feel free to contact her for any, if you would like to contribute to this working group or participate in any future surveys. Also, if you would like to keep updated on development of this particular topic on energy and power aware job scheduling, please do subscribe to this Google group. It's a mailing list right there. And that's it. Thank you. Hopefully this should lead to better collaborations in the future. Please do get in touch. Thanks.